Hi, hi. This is going to be the sixth session on infinite series. We are continuing with our study of, can you believe, infinite series of non-negative terms. Okay, right. So let us get started. Yeah, as usual, this is title infinite series 6. Reference as earlier. This is my channel, YouTube/C convergence. You can download the list of videos from in my channel from here because they are listed in the order. Okay, each subject wise, right, linear analysis, linear algebra, topology, etc., and in that again separate playlist like for sequences, real number system, or continuity, like in order, and within that the order of video. So it will be very good for self-study. Okay, so the first thing we want to talk about today is the so-called integral test. Okay, what does it say? Suppose I have, let us say, 1 to infinity, okay, a function f from to r. Okay, assume that 1 f is non-negative, therefore it takes values in 0 to infinity, and 2 f is decreasing, right? That means x is greater than y, implies fx is less than fy or less than or equal to. Okay, these are the two conditions, right? Then let an be f at n for all natural number n. Now I have two things: infinite series summation n greater than or equal to 1, and I also have this thing which is 1 to n f of t dt. Okay, this is the limit over n. Limit 1 to n f of t dt. So if it exists, one usually denotes by 1 to infinity f of t dt. Okay, this object is defined by this. This is what is called improper integral. Okay, anyway. So what the theorem wants to say is that, okay, this converges if and only if limit n of 1 to n f of t dt converges. Right? The proof is extremely simple. Let us just have a look at the picture. So this is, let us say, 1. So it's something like this. Okay, this is y equal to f of t. Right? Now this is my 1 and this is my 2. Okay, and in general this is my n and this is my n plus 1. Right? Now let us look at this. Okay, what do I know about the integral n to n plus 1 f of t dt? Okay, now notice that f of, on this interval n to n plus 1, I have an obvious estimate. fn plus 1 is less than or equal to f of t is less than or equal to f of n for all t in n to n plus 1. Yeah, therefore this integral n to n plus 1 f of t dt is dominated by f of n into length of the interval, which is 1, and greater than or equal to f of n plus 1 into length of the interval. Do you agree with that? This is n to n plus 1, but that's equal to fn, and similarly this is n to n plus 1, but that's equal to f of n plus 1. This is a constant. All right. Okay, therefore now let me sum it. So if I sum it, n greater than or equal to, okay, let me call it k greater than or equal to 1 to n, what do I have here? I have f of 2 plus f of n plus 1. When a k equal to n, that will be n plus 1. Okay, that will be less than or equal to 1 to, right, 1 to 2, 2 etc. 1 to n plus 1 of f of t dt. But that in turn is less than or equal to f of 1 plus f of n. Yeah, that means I have the following thing. This is Sn plus 1 minus a1 is less than or equal to 1 to n plus 1 of f of t dt less than or equal to Sn. Right? Now this is very easy. Suppose Sn converges. Right? That means, remember, the Sns are all non-negative. Right? Therefore Sn increases to LUB of Sn. Call it S. Okay. Therefore 1 to n plus 1 f of t dt is less than or equal to S. Yeah, for all n. Therefore limit as n will also be less than or equal to S. Right, because this is an increasing sequence of non-negative real numbers bounded above by S, therefore it converges. Right. Conversely, so what have we shown? Convergence of an implies convergence of limit 1 to n f of t dt. And the converse is exactly similar, because let's look at this. 1 to n plus 1 f of t dominates this. Alright, there, and what do I know? And suppose the limit n to 1 to n plus 1 f of t dt equal to, let us say, a. Okay, right, remember a will again be LUB of these numbers, because these are a increasing sequence of non-negative numbers. Okay, therefore it's LUB. Therefore what do I know? I know that Sn plus 1 minus a1 is less than or equal to a. Right, and remember Sns are increasing again, non-negative terms, therefore it's increasing, therefore it's bounded above. Right, Sn plus 1 is bounded above by a plus a1 for all n, and hence limit Sn exists. Okay, so what have we shown? So we have shown that, okay, if f of n equal to an, fn decreases and f is greater than or equal to 0, then summation fn converges if and only if 1 to n f of t dt, this converges. Okay, this is same as saying the proper integral 1 to infinity f of t exists. This convergence and the limit is called denoted by 1 to infinity. Okay, right, pause, review, proceed. Okay, now there are standard applications. One is, let us look at n to the power p, summation 1 by n to the power, the harmonic p series. Right, if I define f from 1 to infinity to r, so that f of x equal to x power p, where p is positive, right, this makes sense. Maybe I wanted n, therefore let's say 1 by x to the power p, 1 by x to the power p. Yeah, therefore what is f at n? 1 by n to the power p. Very good. Yeah, so of course f is non-negative, f is decreasing function. Okay, because p is positive. Right, now does this converge? 1 to n f of t dt. What is this? This is 1 to n, okay, x power minus p dx, or t power minus p dt. Right, by the usual calculus thing, this is nothing other than x power minus p plus 1 by minus p plus 1. So I have to assume p is not equal to 1, because this must make sense. Okay, 1 to n. Right, So when that, this is going to be 1 by 1 minus p, right, minus when x equal to 1, when x equal to n, that's going to be n to the power minus p plus 1 by 1 minus p. Yeah. So whether it converges, all right, if minus p plus 1, that is minus p plus 1, which is 1 minus p, okay. So what do I want? I want to know whether it is converges. Oh, just make sure I did it correctly. Okay, I want this to be convergent, right? So when does this converge? Yes, then my p minus 1 should be negative, right? If you understand, if my n1 is positive, n to the power that will shoot to infinity. Therefore, this must be less than 0. That means p is less than 1. Therefore, 1 to infinity 1 by x power p dx exists if p is greater than 1, right? Therefore, what do I get? I get 1 by n to the power p is convergent if p is greater than 1. Okay. For a similar reason, if p is less than 1, this is divergent. Why? Because what do I have? N to the power 1 minus p by 1 minus p. I hope I am right. But for a fixed constant minus 1 by p. Okay. Minus 1 by 1 minus p possibly. Yeah, I hope I am right. Okay. Alright. Okay. Now what do I know? So if p is less than 1, 1 minus p is positive, therefore n to the power this will go to infinity. This diverges to infinity, therefore this is 1 to infinity x power minus p dx for p less than 1, 0 less than, diverges. And therefore this also divergent. Okay. Now come to the last result on positive series which I want to talk about is this. So let me look at an. An's are non-negative terms. Okay, right. So to talk about the convergence of an infinite series, I kept on insisting what you should look at is the partial sums, because the way we define the sum of infinite series convergence is by sequentially ordering a1 up to an, I get Sn. Therefore, I get Sn plus 1, I get Sn plus 2. Therefore, limit, okay, if the sequence of Sn as n goes, okay, whether it exists, then I call it the limit. That means essentially I am sequentially ordering the number. That is what intuition says, right? And I said you cannot change the order because things may go wrong. We will look at examples of that kind. We have already looked at examples of a divergent series in which the ordering really mattered, but even in convergence series it matters. We will look at example in the next 1 or 2 lectures. But notice that, okay. Now what I am going to do is something very interesting. If I am dealing with an infinite series and non-negative terms, okay, I can kind of sum them up in any fashion. What does it mean? So let f be a finite subset of n. Yeah, hereafter f will also stand for finite subset, right? Let me look at sf to be summation a n where n is in f. For example, if my f is 1, 17 and 12 and 10 to the power 90, then this will be a1 plus a17 plus a12 plus a10 to the power 90, like that. And notice that these are our finite sum, and therefore the order in which they occur does not matter at all. Do you understand that? Yeah, okay, right. Now let us assume summation an, okay, converges. Let us say s equal to summation an. What does this mean? This s is the LEB of Sns. Alright, okay. Now for any f, a finite subset of n, remember whenever I said f is finite, okay, I will not repeat, remember that. What is the relation between sf and s? You see that my f is a finite set, therefore there exists n, a natural number, such that for all k in f, k is less than or equal to n. Do you accept it? Because there are only finitely many terms. So take capital N to be the maximum of elements in f, for example. Yeah? Okay. Therefore, SF is less than or equal to Sn. Remember, Sn is nothing other than S of 1 to n. Call it Fn to be 1 to n. Then this is Sn is nothing other than S of Fn. Do you agree? Accept it? Because these are all non-negative terms, therefore this is. Do you follow that? But this Sn is less than or equal to S, because S is the LUB of Sn, right? Or partial sums, right? Therefore, what do I have got? S is an upper bound of SF, where F union is a finite set. Would you accept it? Yeah? Right. Okay. So, therefore, this set of real numbers, this is a subset of real numbers, non-empty set of real numbers, actually non-negative real numbers. This is bounded above by S. Therefore, let T be the LUB of S of F. Right? So, what is the relation between T and S then? Because T is the LUB of SF and S is an upper bound of SFs. Therefore, T is less than or equal to L. Right? Now we claim, okay, we claim T equal to S. That is, we will prove S is less than or equal to T. Why is that true? Yeah, let us look at. Now, what is S? S is LUB of Sn's, right? Partial sums, right? Now, Sn is nothing other than S of Fn, right? Therefore, S of Fn, this F is a finite set, therefore this belongs to that set. Right? This number belongs to that set. And T is the least upper bound, therefore this is less than or equal to T. Do you understand that? Therefore, T is a LUB of Sn as n varies over capital N. Right? Therefore, T is greater than or equal to S. Yeah? And we already know S is less than or equal to T. Right? We already proved S is less than or equal to T is less than or equal to. Oh, we proved T is the least upper bound, T is less than or equal to S. I have to prove S is less than or equal to T. Okay, sorry. Okay, sorry. Let's. Okay, so what do you want to prove? We want to prove S is less than or equal to T. Therefore, I want to prove T is an upper bound. Yeah, okay. That's done. Yeah, that's what we did. Yeah, T is an upper bound. Okay. Yeah. Therefore, S is less than or equal to T. Yeah, we proved it. Yeah. Yeah, we proved earlier T is less than or equal to S. And now I proved S is less than or equal to T. Therefore, S equal to T. Right? So, let me summarize. So, ANs are non-negative. Let us assume AN is convergent. Then, this sum AN, which is nothing other than LUB of partial sums Sn, is nothing other than LUB of SF, where F is a finite set. So now notice that SF is completely unordered. It's just a finite set. As I wrote, there need not be any order. Okay, and it need not be any sequence also, right? F may not be something like starting from 1 to n or nothing of that kind. Okay, so this is some kind of unordered sums. In spite of that, okay, I get the sum. Okay, learn this well, because when you go to learn Lebesgue measure theory, abstract measure theory, integration, and the corresponding integration, okay, this is what is needed. This approach to integral is what is needed. Okay, so please pay attention. This is usually not in the class, okay, in the typical course, but learn it well. Okay, now I think that's enough. Is there anything else I would like to say about that? I think I can keep on saying, but that's more enough. Okay, learn this well. The other things you can figure out by yourself. Okay, now let an be a sequence of real numbers. Okay, not necessarily non-negative. It could be, or it could even be a sequence in C. Right? So let an be the associated infinite series. Okay, and therefore if I define Sn to be a1 plus an, and if an converges to S, Sn converges to S, then S is denoted by summation an, and I say this is convergent. This is all we have seen so far. Okay, so I am just back to arbitrary an, no assumptions about an. In fact, ans can also be complex numbers. If you are not very comfortable with complex numbers, ignore. It could be any real number, so positive, negative, 0, anything. Okay, good. So I say the infinite series an is absolutely convergent if the series of positive terms, non-negative terms, is convergent. That is, the series of absolute value terms, that is summation mod an is convergent, I say is absolutely convergent. Is the definition clear? Yeah? Right. So, the first thing is, what we want to prove is a very easy proposition. If summation an is absolutely convergent, then summation an is convergent. And not only that, okay, then we can relate the absolute value of the sum an and the sum mod an. Okay, this also we can do. Don't worry about what it is, we will do it in a minute. So when an is absolutely convergent, I want to say an is convergent. Okay, so let Tn be the partial sum of the series, absolute value series. Okay, these are the partial sums of mod an, and let Sn be the partial sums of this series an. So to show the infinite series an is convergent, what I have to show? I have to show the sequence of partial sum Sn is convergent. But remember, Sn is a sequence of real numbers or a complex number. So we have a Cauchy criterion. What does the Cauchy criterion says? A sequence of real numbers or complex numbers is convergent if and only if it is Cauchy. Right? So enough to show Sn is Cauchy. Is that clear? So what does that mean? To show Sn is Cauchy, what does it mean? Take n greater than m, then I have to estimate Sn minus Sm. Right? But what is Sn minus Sm? This will be 1 to n and this will be 1 to m. Therefore, I will be left with an plus an minus 1 plus am. Okay, let us write it the standard way. Sorry, am plus 1 plus am plus 2 plus an minus 1 plus an. Alright, so I have to estimate this. Now, but that is equal to mod am plus 1 plus mod am plus 2 etc plus mod an. What is the obvious estimate for this? Triangle inequality. Therefore, that is less than or equal to mod am plus 1 plus mod am plus 2 plus mod an minus 1 plus mod an. But do you understand what this is? This is nothing other than Tn minus Tm. Is it correct? Yeah. Now what do I know about Tn? Of course they are increasing, but most importantly this is convergent. Therefore Tn is Cauchy. Alright? Are you following? Therefore, if you give me an epsilon positive, I can choose an n natural number so that for n greater than equal to m greater than equal to capital N, mod Tn minus Tm, but this is same as Tn minus Tm because Tn is increasing, n is greater than equal to m. Okay, this is less than epsilon, right? Therefore, what do I get? For all n greater than or equal to m greater than equal to n, mod Sn minus Sm is less than epsilon. That means Sn is Cauchy. Therefore, Sn is convergent. Isn't it great? Very good. Now I want to know the relation. Let us look at mod Sn. What is the obvious estimate for this? This is less than equal to mod A1 plus mod An. Yeah? But this is nothing other than your Tn. Right? Now what do I know? Tn's are convergent to T, and therefore T is the LEB of Tn's. Therefore this is less than equal to T. Do you understand that? Okay, therefore what I have shown is for all n, mod Sn is less than equal to T. Right? Now we know Sn converges. Right? So let S equal to limit Sn. Yeah? Now from algebra convergence sequences we know that if Sn converges to S implies mod Sn converges to mod S. Is that clear? Yes. Therefore, but then mod Sn is less than equal to T for all n, right? And I know mod Sn converges to mod S. Therefore, what do I know? From this I know mod S is less than equal to T. Are you following? Yeah. This says Sn lies in the interval minus T2 plus T. This is a closed and bounded interval. Therefore, Sn converges to S. Therefore, S will also lies in this interval. Therefore, mod S will be less than equal to T. Right? But what is mod S? Mod S by definition is same as saying modulus of An. Okay? That's less than equal to T, but T is same as mod An. Yeah? So, as a mnemonic, you can think of this as a triangle inequality for infinite sum. Why? Because it says summation mod An, let me write it, mod A1 plus A2 plus An dot 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 is less than equal to mod A1 plus mod An dot dot dot. Okay, that's what it says. Right? Okay. So what have we shown? We have shown two things. If the infinite series An is absolutely convergent, then the original infinite series summation An is convergent, and the absolute value of summation An will be less than equal to summation of modulus Ans. Okay, in the case of convergence. Is that clear? So this is, with this I just wanted to give you my trick or tip, okay, a trade secret. That is what usually analysts will do. Okay, if you give me a series An, if I want to look at convergence, the first and the foremost trick I will use will be, I would like to check whether mod An is convergent. Okay, A and B complex numbers or real numbers, I don't care, I will check. Okay, and this is a positive series. For positive series, we have a lot of results. We have the most important thing is comparison result with geometric series, or if you want ratio test, root test, or integral test. Okay, so the easy tests are available for absolute convergence, that is for a series, infinite series of non-negative terms. So use that. So once I know this is convergent, this is going to be automatically convergent. That's it. I also have an estimate in modulus for the sum. Do you follow that? This is a standard. Very rarely, okay, they will try to use various other tests. Okay, they will first check for absolute convergence, to check absolute convergence, they will try for your ratio root test, or okay, directly go for the thing. Okay, you try to estimate it by okay the mod ANs and in compare it with some geometric series. Therefore, comparison in geometric series, as I said, that's a mother of all tests. So you get the result. As a, if you are lucky. See, in most often higher analysis, you will be dealing with sequences such that the corresponding associated infinite series is absolutely convergent. Okay, so therefore, only in Fourier analysis, you will have problem, because there it will be summation an cos nx, sin nx, etc., etc. Okay, there you cannot do any of these things. Okay, that will come later. Okay, this is the trade secret. Remember, the first thing, whenever you are given infinite series, you should look for absolute convergence by some other very easy test. If it works, you are lucky, you are happy, the job is done. Okay, let me end the lecture with the last result. Okay, the converse of the result is true, is false. That is, if an may be convergent, but mod an is not convergent. Okay, absolute convergence implies convergence, but okay, this may not be the case. Okay, if the series is absolutely convergent, it is convergent. But if the series is convergent, the series may not be absolutely convergent. Okay, please compare this with sequences. If an converges to a, mod an will converge to mod a, but if mod an converges to mod a, will not imply an converges to a. You see that there is a mismatch in these two results. Yeah, please understand that. Okay, the standard result is a usual alternating series. So let Tn be non-negative and Tn decreases to 0. Right? Now let An be minus 1 to the power n minus 1 Tn. Therefore, it's going to be T1 minus T2 plus T3 minus T4. That is the infinite series. So I have the infinite series An. Yeah. So I want to say, okay, this series is convergent. What is the assumption? Tn's are non-negative. Tn decreases to 0. From Tn I form alternating thing. T1 minus T2 plus T3 minus T4 and so on. That's an infinite series I get. That series is convergent. This is called alternating series. Okay. So let S2n, let me look at only the even partial sums. Okay. This is going to be, you can see, T1 minus of T2 minus T3, okay, minus of T4 minus T5, etc. Yeah. Now T2 is greater than or equal to T3, therefore this is positive, this is negative, and this is negative. You understand that? Yeah. And what is the last one? That will be T2n minus T2n. Yeah. So that will be less than T1. Therefore, S2n is bounded above. Yeah. Right. Next, let us rewrite it. Remember, this is where we are using the fact it's a finite thing. This is, I can write as T1 minus T2 plus T3 minus T4 plus T2n minus 1 minus T2n. This is greater than or equal to 0. This is greater than or equal to 0. This is greater than or equal to 0. Because Tn's are decreasing. Right? Therefore, what do I know? S2n is increasing sequence and bounded above. Right? Therefore, S2n converges to some, call it, I will call it S, okay, for the time being, okay, converges to some real number S. I claim that Sn itself converges to S. So what do I know is the sequence of even partial sum converges to S. Now I want to claim Sn itself converges to S. So what is that I have to do? If you give me an epsilon, I have to show some xk minus s is less than epsilon if k is very, very large. Alright? If k is even, I know that because s to n converges to s, therefore I can always make it. Alright? So the problem is what happens to odd. So as usual, I will not fix capital N, etc. I will just like that work with that and we will arrive at the result. So let us look at, okay, s2 s minus s2 n plus 1. Yeah, right. But this I can do as s minus s2n plus s2n minus s2n plus 1. But that's less than I could s minus s2n plus s2n minus s2n plus 1. Yeah, okay. I hope I am is there any smarter way of doing s minus s2n s2n? I think this should be enough. Okay, right, that's fine. Yeah, now what do I know about this fellow? Remember, what do I know about s? Tn converge to 0. That means Sn also, okay, the ans converge to 0 because ans are minus 1 to the power n minus 1 Tn. Okay, remember an converges to 0 if only mod an converges to 0, but mod an is nothing other than Tn. Right? Is that okay? Therefore, what do I know? I know that there is an n, okay, so that for all n greater than or equal to n, capital N, this term, sorry, this is not s2n, yeah, let me write, s minus s2n plus 1 is s minus s2n, yeah, what is s2n plus 1? Okay, remember s2n plus 1 will be s2n plus the last an, a2n plus 1. a2n plus 1 is what? That is minus 1 to the power 2n into tn, which is t2n plus 1. Yeah, right? Therefore, this object I can write it as plus a2n plus 1. But that's less than I could s minus s2n plus mod a2n plus 1. Okay, but that is mod s minus s2n plus tn, t2n plus 1. Yeah, now I am through. Why? Given epsilon positive, there is an n, so that s minus s2n, if n is greater than or equal to capital N, this will be less than epsilon by 2. And the same for the same n, since Tn converges to 0, okay, for n greater than or equal to n, Tn plus 1 modulus, which is same as Tn plus 1, 2 Tn plus 1, this is less than epsilon by 2. Therefore, the whole thing is less than epsilon. Yeah, so I have proved, okay, the alternating series summation minus 1 to the power n minus 1 Tn, when Tn's are positive, Tn are decreasing, is convergent. Right? So a special case is minus 1 to the power n minus 1 by n, where Tn is 1 by n. Now Tn's are positive, they converge to 0, therefore I know this is convergent. But what is the absolute value series? This is divergent. Right? So if a series is absolutely convergent, we know the corresponding infinite series summation n is convergent, but the converse is not true. So on the way, we also looked at the so-called standard alternating series. Okay, we looked at it and did that. In fact, later we are going to say that, therefore this standard alternating series summation minus 1 to the power n minus 1 by n, we know it's convergent. But if I group terms okay differently, the series may still converge, but the sum will be different from the original sum in the standard order. Okay, this is what I just said about half an hour ago. We will look at it later. Okay, don't be in a hurry. Please go through, learn it well. We will meet again.